Welcome to The Explainer. Today, we are cracking the code behind how scientists see, build, and innovate on a microscopic level. We're going to translate some pretty complex stuff into a story that just makes sense. So, if you've ever tried to read a scientific paper, you have probably slammed into a wall of acronyms just like these, right? It can feel like you're staring at some kind of alphabet soup, a secret language that's just designed to keep you out. But what if I told you that's not what it is at all? What if this isn't a secret language, but actually a toolkit, a collection of incredibly precise instruments that scientists are using every day to see, to understand, and to literally build the future? All right, let's get into it. So here's the plan. First, we'll tackle what looks like science's secret language. Then we're going to explore the tools for seeing a world you can't see with something called microscopy. After that, we'll learn how to decode chemical clues with spectroscopy, and finally, we'll see how it all comes together to form the toolkit for tomorrow. Okay, so how in the world do scientists actually see things that are impossibly small? I mean, stuff that's way, way beyond what a normal microscope could ever show you. Well, they use techniques like microscopy to get a front-row seat to the nanoscale world. A real heavy hitter here is the scanning electron microscope, or SEM for short. Now, instead of using light, it shoots a focused beam of electrons to scan the surface of a material. What you get back is this incredibly detailed, almost 3D-like map of its terrain. And what SEM can show us is just wild. Scientists are using it to see everything. The fine-grained texture of a new dental filling, the tiny, tiny cracks that are starting to form in a piece of ancient art. They can see the structure of a new waterproof coating on fabric, or even watch how an orthodontic glue holds up when you hit it with acid. So you can basically think of it as the ultimate quality control camera. It lets scientists zoom all the way into the atomic level just to make sure that the brand new materials they're building are structured exactly the way they're supposed to be. And that level of precision is everything. I mean, some researchers are using lasers with wavelengths of just 800 nanometers. To put that in perspective, that is about 100 times smaller than the width of a human hair. They use them to literally write patterns onto surfaces, and then they use SEM to make sure they got it right. Okay, let's move on to the next tool in our kit, because seeing what something looks like, that's really only half the story. If you want to truly understand a material, you also have to know what it's actually made of. And this is where spectroscopy comes in. If microscopy is the eye that lets you see the tiny details, think of spectroscopy as the chemical nose. It's how you read an object's unique chemical fingerprint to figure out its exact composition. And the star player here is something called FTIR. The way it works is pretty cool. It shines infrared light on a sample and then measures how the molecules in that sample absorb the light. Because different chemical bonds wiggle and vibrate in their own unique ways, FTIR can create a spectrum, a fingerprint really, that tells you exactly what molecules you're looking at. And honestly, based on the research we looked at, FTIR is kind of the MVP. It's one of the most versatile and essential tools they've got. It popped up in almost every single study, which shows you how valuable it is in all sorts of fields, from material science to biology and even art history. Its flexibility is just incredible. So in one lab, a scientist might be using it to figure out why an ancient lacquer painting is slowly falling apart. At the same time, in another lab, someone is using it to confirm that life-saving proteins have properly attached to a medical implant. It can even spot the tiny chemical changes that happen when you cut a piece of wood with a laser. So here's the most important point. These amazing tools are almost never used alone. The real magic, the stuff that really pushes innovation forward, happens when scientists combine them. They form this complementary toolkit where each instrument answers a different but totally vital question. It's a powerful 1-2 punch. A scientist can use SEM to see the beautiful, intricate structure of a new material. And then, in the next step, use FTIR to confirm that its chemical makeup is exactly what they designed it to be. One tells you how it looks, and the other tells you what it is. And you can see this synergy happening everywhere in the real world. For example, to create stronger dental fillings, researchers use SEM to see that nanostructure and FTIR to confirm the chemical bonds. For making self-cleaning fabrics, they'll use SEM to look at the nanoparticle coating, another tool called EDS to identify the elements, and of course FTIR to analyze the chemistry. From preserving art to building better medical devices, it's this combination of tools that really drives progress. So the big takeaway here is that this whole alphabet soup, the SEM, the FTIR, all of them. It's not a barrier that's meant to confuse you. It's actually a super precise, descriptive language. It's the language that tells the story of how modern innovation really, truly happens. From biocompatible implants that can heal our bodies, to more durable materials for our cities, to new ways to preserve our history, this toolkit is literally building our future, one molecule at a time. The only question left is, what do we want to build next?